here's another thing that can help you out in doing problems like this, is you can work in other coordinate systems. So let me just show you how much easier this would have been in another coordinate system, and I'll show you why. And we'll even, let's see. So consider same question in parallel and perpendicular to the ramp. All right, so basically just we could turn our coordinate system and say, let's work in this perpendicular direction and parallel direction. I'm even going to use those like they're letters. Okay? You might see somebody say, let's just redefine x and y this way. Could do that, but then the notes aren't, then it'll look the same. Some people might say put x prime and y prime, but those primes give people heart palpitations for some reason, so we're not going to do that. I'm going to call them parallel and perpendicular. Okay? So the exact same problem, let's just solve it real quick. Let's look, and now we're going to do it kind of with the notation we would normally use. Parallel direction. It's not moving in the parallel direction, right? It's just sitting there. So let's just say, well, what's the deal? Well, we know that the normal force in A is just along the parallel direction. So we don't have to do much. We just say in A. Is that a component or a magnitude? I think it's a magnitude. And then we say, well, what about the component of mg in that direction? Okay, so mg, and we're thinking about this direction, so we got to get a component like that for mg and like that for mg. All right. So this would be, let's see, so one thing you just got to eventually learn is that this theta equals that theta. Right? If you can't see that, think about what if theta went towards 0. If theta went towards 0, this angle would get really small, and this angle would get really small. So think about what angle shrinks to 0, if you can't tell that that's theta. And then you'd say, well, then this component is mg cosine theta, and this component is mg sine theta. So there you go. You look at that, and you say the component down the ramp is mg sine theta, and it's the opposite direction is A, so I'm going to put a negative sign on it. Now you're doing it the old way. Okay? If you want to do it the proper way, you'd say it's plus mg sine theta, and theta is negative. Right? Oh, it's in the negative direction, or something like that. Right? You'd find a way to get there. I don't even know, because I don't really do it the full four-board way. We all kind of do it this way. So if we're doing it this way, basically we are calculating the negative in our head. Okay? That's what we're doing. Yeah, let's see, the technical answer, I don't know, let's not get into it. We don't have time to do every one that way. So the answer is NA equals mg sine theta. Well, that was easy. It took a lot longer to do the other time, didn't it? And what about y? Some of the force, the perpendicular direction, also not moving. Therefore, we say NB. Well, that's in the positive perpendicular direction. There we go. Right? It's got a perpendicular to the surface. It's got to just be NB. And which way is gravitational? Well, it's the other way. Right? It's down. So we say minus mg cosine theta equals 0. And we say, oh, NB, the magnitude of MB is mg cosine theta. So why was it so much easier? Well, one reason is I didn't do the full formal notation, but the other reason is here we only had to break one vector into components, g. And here we broke two vectors into components, normal A and normal B. And it's because we broke two vectors into components we had to do all that algebra. If we just break one vector into components, then we're just done right at the beginning. Okay? So if you think about a problem of a block on a ramp, and later it'll be sliding, and there'll be friction, and normal forces, and wind, and tornadoes, and all this stuff will be blowing it around. All those forces will be this way. Right? Friction's this way. Somebody pushing it is this way. A spring is this way. A rope is pulling. Everything is this way. The only thing this way is g, mg. So it makes sense to do your problems in this coordinate system, because then you don't have to deal with one vector's components. And you can see, even in this simple problem, how much easier it was to work in this tilted coordinate system. Okay, so you can call it x prime, y prime, you can call it x and y, you can call it perpendicular parallel, but whatever you want to call it, but it is actually easier. What angles are the same for the different coordinate system? It's the same angle, right? So if this thing is on a ramp tilted at theta, then you just rotate your coordinate system by theta. So there's really still just one angle, it's just theta. That's the same theta. Okay. Okay. So I didn't do all the details here. So hopefully you see the connection, and hopefully it helps you assign negative signs. Okay. Cool. Wow.